Welcome back to Talk Tensors, listeners.
Yeah.
Today we're going to be taking a deep dive into a paper that has the potential to really kind of like revolutionize reinforcement learning.
Oh, wow.
Yeah, it's called From Sparse to Dense, Toddler-inspired Reward Transition in Goal-Oriented Reinforcement Learning.
Interesting.
And it's causing quite a buzz in the AI community.
It's a fascinating paper. It draws inspiration from a rather unexpected source.
Oh, really?
Toddlers.
Toddlers.
Yeah.
I'm intrigued, but also a little terrified knowing how much those little humans get into.
Well, hold on to your hats because this paper suggests we can learn a lot about efficient learning from those tiny explorers.
Okay.
Think about it. Toddlers start out exploring the world with what the researchers call sparse rewards.
A sparse reward.
They're playing experimenting, but not necessarily working towards a specific goal.
So like a baby banging on a toy piano.
Yeah.
They're just enjoying the sensory experience and the immediate feedback of sounds, not composing a symphony, right?
Exactly. It's pure exploration.
Yeah.
But as toddlers grow, they start to develop more focused behaviors like stacking blocks or trying to fit shapes into the right holes. And when they achieve those goals, they get a much clearer sense of reward, that satisfying feeling of accomplishment.
Okay. I'm starting to see where this is going. So the paper argues that we can make reinforcement learning agents learn more effectively by mimicking this developmental shift from exploration to goal-oriented behavior.
Precisely. The paper proposes transitioning from sparse rewards where feedback is infrequent to dense rewards, where feedback is more frequent and directly tied to achieving a specific objective.
Okay.
They call this the sparse to dense reward transition, or S2D for short.
S2D, got it.
Yeah.
And they actually tested this S2D approach in a bunch of different RL environments.
That's right.
What kind of results did they see?
Well, they tested S2D in a range of environments, robotic arm manipulation, the classic lunar lander and cart pole control problems, and even visually complex 3D mazes. What's remarkable is that across all these different scenarios, the agents trained with the S2D reward strategy consistently outperformed agents trained using other methods.
So faster learning, A&D, better performance. That's a pretty compelling combination.
It is.
But I have to admit, the toddler analogy, while intriguing, still feels a bit abstract to me.
Yeah.
Can you unpack exactly how this sparse to dense transition works in practice?
Let's dive a little deeper into the mechanics of it. The paper employs a technique called potential-based reward shaping, or PBRS, to manage this transition.
Okay.
Now, PBRS isn't new, but the way they've utilized it here is quite innovative. Imagine you're training an agent to navigate a maze.
Okay.
In a purely sparse reward setting, the agent only gets a reward when it reaches the exit.
Right.
But with PBRS, you can give the agent additional rewards based on how close it's getting to the goal, even if it hasn't reached the end yet.
So it's like giving the agent breadcrumbs, little nudges along the way to keep it motivated and guide its exploration.
That's a great way to put it.
Yeah.
PBRS helps smooth out the learning process, making it easier for the agent to discover effective strategies without getting stuck in dead ends.
Okay, so PBRS is the secret sauce that makes this whole toddler-inspired thing work.
It's a key ingredient, that's for sure.
Yeah.
It allows for a smooth transition from exploration to exploitation, mimicking the way toddlers gradually shift from playful experimentation to more focused, goal-directed behavior.
This whole conversation is making me rethink how we approach learning, not just for AI, but maybe even for ourselves. I mean, we all start as toddlers exploring the world with that same sense of wonder and curiosity. Maybe there's something to be said for embracing a bit more of that free-spirited exploration, even as we get older. But let's not get too philosophical just yet. We've got a lot more to uncover about this S2D approach.
Absolutely. And to understand the significance of S2D, it's helpful to look back at the history of exploration versus exploitation in reinforcement learning.
Okay, let's take a quick detour into the past.
All right.
What were some of the earlier approaches to tackling this fundamental challenge in RL?
Well, early on, a lot of RL algorithms relied on relatively simple exploration strategies, like epsilon greedy, where the agent randomly chooses an action with a small probability epsilon and otherwise exploits its current knowledge to choose the best action.
So it's like flipping a coin every now and then to decide whether to try something new or stick with what seems to be working.
Exactly. And while epsilon greedy can be effective in some cases, it can be quite inefficient, especially in complex environments where random exploration is unlikely to stumble upon rewarding actions.
Yeah, it makes sense that random exploration wouldn't be the most efficient way to learn. What were some of the other approaches that researchers explored?
As the field matured, researchers started to develop more sophisticated exploration strategies. One approach that gained a lot of traction was optimism in the face of uncertainty. The idea here is to encourage the agent to explore actions or states that it hasn't visited much before essentially giving it a bonus for trying new things.
Okay, that sounds kind of like how toddlers are drawn to anything new and shiny.
It's a good analogy. This approach leverages the idea that the agent's initial knowledge is incomplete, so it's worth being optimistic about the potential rewards of unexplored options.
Okay, so we've got random exploration and optimism-driven exploration. Were there any other major breakthroughs in this area?
Another influential approach involved incorporating intrinsic motivation into the reward function. Instead of relying solely on external rewards provided by the environment, agents were also rewarded for things like discovering novel states or reducing their uncertainty about the world.
That reminds me of a paper I read a while back where they trained agents to play video games by rewarding them for exploring new areas of the game world, even if those areas didn't offer any points or power-ups.
Yes, that's a great example of intrinsic motivation in action. And those curiosity-driven agents turned out to be surprisingly good at mastering the games, even without any explicit goals.
So it seems like there's been a lot of progress in designing exploration strategies that go beyond simple randomness. But how does the S2D approach fit into this historical context? Is it building on these earlier ideas or taking a completely different direction?
It builds on these earlier ideas while introducing a novel perspective.
Okay.
What's unique about S2D is that it focuses on the timing and structure of the reward signal. Instead of trying to come up with clever ways to encourage exploration explicitly, S2D implicitly guides exploration by strategically transitioning from sparse to dense rewards as the agent learns.
So it's more about shaping the overall learning process than tweaking the reward function itself.
Exactly. It's like providing a scaffold for the agent's learning, starting with a more exploratory phase and gradually shifting to a more goal-oriented phase as the agent gains experience.
That makes a lot of sense. Now, earlier you mentioned that the S2D approach actually led to a smoother loss landscape. Can you remind us what a loss landscape is and why its smoothness is important for effective learning?
Think of the loss landscape as a 3D map where the height of each point represents how well the agent's neural network is performing. The lower the point, the better the performance. The agent's learning process can be visualized as navigating this landscape, searching for the lowest point, which represents the optimal solution.
Okay, so if the landscape is smooth and gently sloping, it's easier for the agent to find the best solution.
Exactly. A smooth landscape means the agent can gradually descend towards the optimal solution without getting trapped in local minima, those pesky valleys where the agent might think it's found the best solution, but there's actually a better one just over the next hill.
Got it. Okay, that makes sense. But how does the S2D approach actually lead to a smoother loss landscape? Is it just a happy side effect, or is there something more fundamental going on?
That's a great question. It's not just a coincidence. By starting with sparse rewards, the S2D approach encourages the agent to explore a wider range of states and actions early on. This initial exploration helps the agent build a better internal representation of the environment, which in turn leads to a smoother loss landscape.
So it's like the agent is building a more detailed map of the terrain, making it easier to navigate later on when it's time to find the optimal path.
That's a good way to think about it. And this connection between early exploration and smoother loss landscapes is actually supported by some fascinating findings in neuroscience.
Oh, I'm always up for a little brain science. Tell me more.
Well, there's a growing body of research suggesting that early exploration and play might be crucial for the development of cognitive maps in the brain, those internal representations of the spatial environment.
So just like those little explorers we were talking about earlier, the agents that are allowed to roam freely in the early stages of learning might actually be developing better cognitive maps that help them navigate more effectively later on.
That's the idea. And it highlights the potential of drawing inspiration from developmental psychology to improve our understanding of AI learning.
Yeah, I'm really starting to see how this toddler-inspired approach could be a game changer for reinforcement learning. But I'm also curious about the specific findings in the paper. What kind of insights did they glean from those robotic arm and maze navigation experiments? What did the data actually show?
Well, in the robotic arm experiments, they tested various manipulation tasks. Things like reaching for a target object, grasping and moving objects to specific locations, even stacking objects. Essentially the kinds of things a toddler might try to do with their own little hands.
Oh yeah, I can see that. It's amazing to think that we can train robots to do these tasks that seem so intuitive for us humans. but I imagine it's not as easy as it looks for a machine.
It's definitely a complex challenge, but the S2D approach showed promising results.
Okay.
The researchers observed that the robotic arms trained with S2D learned these manipulation skills significantly faster than those trained with conventional reward strategies.
So faster learning, just like in the other environments they tested.
Yeah.
But did they also see improvements in the quality of learning, like better generalization to new tasks?
That's the exciting part. They found that the S2D agents were indeed better at generalizing.
No.
For instance, if they trained an agent to reach for a red block, it was then more likely to be able to reach for a blue block without needing as much additional training.
It seems like that initial phase of sparse rewards, where the agent is encouraged to explore freely, is really paying off in terms of building a more robust and adaptable understanding of the task.
Precisely. It's like they're developing a deeper understanding of the mechanics of manipulation, not just memorizing a specific sequence of actions.
Fascinating. Okay, let's move on to those maze navigation experiments. You mentioned they used the VizDoom game engine to create these visually rich 3D mazes. What did those experiments reveal about the effectiveness of S2D?
These experiments were particularly interesting because they required the agents to learn from raw visual input instead of having access to a map or coordinates. The agents had to navigate the maze based solely on what they saw through the eyes of their virtual avatar.
That sounds like a much tougher challenge, much closer to how we humans navigate the real world.
Exactly. And the S2D agents rose to the challenge. They learned to navigate the mazes much faster than agents trained with other reward strategies. They were also better at generalizing to new mazes they hadn't seen before.
So once again, we see evidence that the S2D approach promotes both faster learning and better generalization. It's really starting to feel like a winning formula.
It's certainly a promising direction, and the researchers didn't stop there. They also explored how the S2D approach impacted the learning process at a more fundamental level. They analyzed the activity of the agent's neural networks.
Okay, this is where things get really interesting. Tell me more about what they found when they peeked inside those artificial brains.
One of the key insights came from analyzing the hidden state vectors of the RNN used in the Playroom maze environment. These vectors essentially capture the internal representation of the environment that the agent learns. What they found was that the S2D agents showed significantly faster convergence of these vectors compared to agents trained with other reward strategies.
So faster convergence means the S2D agents were learning a more stable and robust representation of the environment.
Exactly. This indicates that S2D might be promoting a deeper understanding of the environment, not just a superficial ability to solve the task.
That's a crucial distinction. We don't just want AI agents that can solve problems. We want agents that can understand the world around them.
Absolutely. And there's more. They also conducted an action frequency analysis, which revealed that the policies learned by the S2D agents were more stable over time.
Stable policies. What exactly does that mean, and why is it important?
A stable policy means that the agent's behavior is more consistent and less prone to erratic fluctuations. This is important because it suggests that the agent is learning a more reliable strategy that is less likely to be thrown off by unexpected changes in the environment.
So it's like the S2D agents are learning to be more adaptable and resilient, which is crucial for real-world applications where things rarely go exactly as planned.
Precisely. The S2D approach seems to be fostering a more nuanced and flexible understanding of the task, leading to more robust and reliable performance.
This has been an incredibly insightful deep dive. We've covered a lot of ground from the toddler-inspired origins of the S2D approach to the specific findings in those robotic arm and maze navigation experiments, and we even delved into the inner workings of those artificial brains to understand how S2D promotes a deeper and more robust learning process. But as always, I'm eager to explore the implications of this research further. It's time for our Novel Notions segment.
Excellent. Let's put on our speculative hats and brainstorm some wild but potentially groundbreaking research ideas inspired by this paper.
This whole S2D concept has me thinking, what if we could apply this to how people learn? Not just make better AI, but better schools, better training programs. Imagine a world where we encourage more exploration and play in the early stages of learning, gradually introducing more structured goals and feedback as learners develop their understanding.
That's a fascinating idea. It aligns with a growing body of research suggesting that play-based learning can be incredibly effective, especially for young children. Perhaps the S2D approach could provide a framework for designing more engaging and effective learning environments for humans as well.
Yeah, it would require a significant shift in our thinking about education, but the potential benefits are enormous. Imagine classrooms designed to foster curiosity and exploration, where students are encouraged to experiment and discover their own paths to knowledge.
It's a compelling vision. And who knows, maybe someday we'll see those toddler-inspired learning environments become a reality, revolutionizing both AI and education as we know it.
That's a fantastic note to end on. Thanks for joining me on this deep dive into toddler-inspired machine learning. It's been a truly thought-provoking exploration, and I'm excited to see where this line of research leads us. Be sure to check out the show notes for a link to the full paper and other resources.
And don't forget to subscribe to Talk Tensors for more deep dives into the fascinating world of machine learning.
Until next time, keep those brains buzzing.